Okay, let's dive headfirst into this, shall we? We're tackling a really a core friction point in operational technology today.
Absolutely. It's that big standards debate.
Exactly. The battle between IEC 61499 and the long-reigning champ, IEC 61131.
Yeah. It's quite the discussion in the industry.
And looking at our sources, articles, white papers, expert comments, you see these like two totally different narratives emerging. On one hand, you've got people calling 61499 revolutionary, essential for Industry 4.0.
The future, basically.
Right. But then you have other very experienced engineers saying, hang on, 61131 already does everything we need.
And that's where the confusion often starts, especially for you, the learner, trying to get your head around this. Franco Antonio Cavadini really hit on it. People often dismiss 61499 as just, another programming language.
Which misses the point entirely.
Completely. If you see it that way, you won't grasp why it might be necessary. So our mission today is really to clarify that 61499 isn't a language. It's more like a blueprint for how computation behaves.
A blueprint for behavior. I like that.
Especially in a distributed world.
That clarity is vital because that initial reaction we see, from folks like Davy DeMeyer or Tim Dunn-Hartog, it often just boils down to skepticism, right?
Right, like why fix what isn't broken?
Exactly. Why add this complexity if 61491 has worked for decades? So let's start there. Why was 61499 even created? What problem was it solving?
Okay, to answer that, we need to rewind a bit, way back actually to the early 90s. Think about James Christensen's work then.
Okay. What was the landscape like?
Honestly, it was chaos. Industrial automation was incredibly fragmented.
Fragmented how? Like different vendors?
Exactly. Every vendor, every system integrator, they basically had their own dialect, their own way of thinking about computation, their own models.
Right. Proprietary systems everywhere.
Which made integration a nightmare. Super brittle, super expensive, migrating systems, forget it.
So the standardizers saw this mess.
And they realized the issue wasn't a lack of programming tools. They had plenty of ways to write code. What they lacked was a universal architectural model.
Okay, so the goal wasn't just like a better ladder logic or function block diagram.
Not at all. The goal was to standardize the meaning, the semantics, of the control system itself.
Regardless of who made the hardware or what specific syntax you used.
Precisely. So if we define 61499 properly, it's fundamentally a framework. Think of it as a semantic contract.
The contract.
Yeah, or an architectural blueprint. It dictates how different bits of computation function blocks interact, how they react to events, how they cooperate across a network.
Okay, so it's not defining the syntax, the actual code writing?
No, that's still largely 61499 domain. 61499 defines the rules for distribution and event handling. It governs how code behaves when it's spread out and reacting to things happening.
Right, how it behaves in a distributed reactive world. That makes sense.
That shift in focus from vendor dialects to a standard model of computation is the absolute key.
Okay, so we've established it's a framework, a model. But to really see why people call it revolutionary, we need to, get a bit technical, don't we?
We do.
How does its conceptual architecture really differ from that traditional 61131 approach we all know?
The difference is architectural, yes, but also temporal. How it handles time.
Okay.
Think about traditional 61131. It's built around that sequential, synchronous scan cycle, right?
Poll inputs, run logic, top to bottom, update outputs, repeat.
Exactly. It works, it's proven, but it's inherently time-locked. Everything happens in that fixed cycle. And it's usually centralized on one PLC.
Like a conductor leading an orchestra, making sure everyone plays their note in strict sequence.
That's a good analogy. Now, 61499 flips that. It's inherently asynchronous and event-driven.
Meaning?
Meaning computation doesn't just run because the scan cycle hit that point. It runs because something happened, an event occurred.
Okay, and how does it manage that?
It does this by treating events as first-class citizens. They're fundamental building block.
Not just data values changing.
No. Instead of waiting for the global scan, these computational units, the function blocks in 61499, only execute when they receive an explicit event trigger.
Okay, and I remember reading the function blocks themselves are different, more sophisticated than in 61131.
Oh, absolutely.
Yeah.
A 61499 function block is much more than just an algorithm. It encapsulates its own internal state machine.
The ECC, right, execution control chart.
That's the one. The ECC defines exactly how the block behaves, which internal algorithm runs based on which incoming event, and what the block's internal state is.
Wow, okay. That sounds like a big deal.
It's a game changer. because it means the logic itself can be stateful, it can be reactive, and crucially, it can be physically distributed across different devices.
Without needing that constant polling or tight synchronous timing between them.
Exactly. The event carries the trigger and potentially the data.
I think I'm getting it. So the ECC inside the function block knows, okay, this event arrived, so run this piece of my logic, and if the result is X, send out that event.
Precisely. And that output event might trigger another function block located, across the factory floor, or maybe even up in the cloud.
That sounds like genuine modularity and distribution baked in.
It is. And this leads directly to that critical separation we mentioned earlier. 61499 forces you to separate what the logic does, the algorithm inside the function block, from where it actually runs.
The distribution part.
Right, the resource configuration, the device mapping. You design the application architecture, how the blocks connect and react once. Then you map that architecture onto whatever distributed hardware you have available.
That gives you portability, presumably.
Unprecedented portability, yes.
And the practical outcome of all this, as some experts describe it, is creating the shared conceptual foundation.
Yes, exactly. It's like everyone agrees on the meaning of the distributed interactions.
So it becomes a common language of meaning, not just a common syntax, enabling engineers, tools, organizations to work together more smoothly.
And that shared understanding pays off in real-world efficiency. Think about what Greg Bucco mentioned regarding complexity and the skills gap.
Right, the shortage of engineers.
By adopting this kind of reusable, standardized architecture, companies can abstract away a lot of the low-level hardware specifics.
So engineers can focus more on the application logic, the actual problem they're solving.
Exactly, which reduces complexity, promotes reuse across different machines or plants, and helps alleviate some pressure from that chronic shortage of skilled automation engineers.
It really does sound like a philosophical shift. You're moving from just defining control loops to defining computational behavior across a whole network.
You are. And it's a shift that's arguably required because, well, the world has changed quite dramatically, hasn't it?
Which brings us nicely to the present day. We're not just building isolated machines anymore. We're deep into the industrial Internet of Things, IIoT, Industry 4.0.
Right.
Talk us through the kind of computational landscape we're dealing with now. It's much more complex.
Incredibly complex and deeply heterogeneous. You've got edge nodes running, say, containerized applications. You've got tiny embedded controllers on sensors. You have virtual models, digital twins running simulations. And then you've got massive cloud infrastructure processing data.
And somehow all these disparate pieces need to talk to each other and function like one cohesive control system.
Precisely. Now, imagine trying to orchestrate that using only a synchronous sequential standard like 61131.
It feels like you need a lot of custom code middleware working.
Massive workarounds,
Why?
often leading to proprietary solutions, system bloat, things that are hard to maintain. It becomes very brittle.
Okay.
And that's why advocates argue 61499 is now crucial. You need a homogeneous semantic framework at that operational technology, the OT level.
A common architectural blueprint.
Exactly. One that lets you orchestrate all those different elements from the sensor right up to the cloud in a seamless way. Without that shared architectural understanding, you're just building point-to-point connections, which are fragile and complex.
So it enables that seamless IoT convergence that Maxence Priovas talked about?
Yes. He argued it provides the structure needed to really foster innovation and improve industrial performance because it standardizes that reactive distributed behavior across the whole ecosystem.
Makes sense.
And Udayanto Dwi at Mojo pointed out the practical side for advanced control, too. 61499 gives you the basic tools needed to easily apply truly distributed algorithms.
So you're not just controlling one motor based on its local sensor.
Right. You might be distributing a complex optimization algorithm across multiple machines, coordinating them in real time based on events happening throughout the system. That capability is just fundamentally beyond the original scope of 61131.
And connecting this back to the business side, Jean-Baptiste Fontaine's point really resonated. He said the true value isn't just the standard itself.
Right. It's the speed and precision of agreements it enables.
Exactly. If systems and the people building them can agree on the semantic meaning quickly and reliably, then collaboration just accelerates.
And faster collaboration is the fastest way to drive progress in the industry. Simple as that.
Okay, this paints a compelling picture for 61499, but we have to address the other side fairly. If the benefits are so clear, why is there still real resistance? We mentioned contributors like Davy DeMeyer and Timden Hartog, who strongly feel 61131 is sufficient. What are their strongest points? The valid counterarguments.
And they are valid, practical arguments. You can't just dismiss them. First and foremost, 61131 is incredibly stable. It's proven technology.
Decades of use. Safety-critical applications rely on it.
Absolutely. Integrators know it inside out. The tools are mature, widely available, understood. And think about brownfield sites, existing factories.
Right, you can't just rip everything out.
Exactly. Modernization has to integrate with all that legacy equipment. Introducing a completely new architecture like 61499 involves a significant cost, a steep learning curve. That can be a massive barrier.
That's a very fair point. If a manufacturer's current system is running reliably and their team is expert in 61131, why go through the pain and expense of changing just to get distribution features they might not even fully utilize yet?
That's the core tension, isn't it?
It seems like pushing 61499 could just add cost and training overhead, especially for maybe smaller manufacturers.
You're absolutely right to flag the cost and stability aspects. 61131 is often sufficient when control is mostly centralized, sequential, and tightly coupled within one machine or cell. But the frustration emerges when engineers try to sort of shoehorn modern distributed requirements into that old synchronous scan cycle model.
Shoehorn. Yeah, I've heard that.
Our sources mention that when integrators really push 61131 beyond its original intent, the resulting architectures can get bloated.
Bloated, meaning complex and inefficient.
Yeah, requiring lots of custom code, complex timing dependencies, constantly working around the standard's inherent limitations just to achieve basic distributed functions.
And that working around time isn't free, is it?
No way. It's pure cost, added complexity, and introduces potential risks. Things get harder to debug, harder to maintain.
So the argument really pivots. It's not about whether 61131 is good. It clearly is for its purpose.
Right.
It's about whether it's the right architectural foundation for new systems that are inherently flexible, distributed, and maybe involve lots of different types of devices. Greenfield projects, maybe?
Exactly. And that's where Stephen Maltby's point comes in strongly. He highlighted that system integrators, especially those building complex, bespoke machinery or flexible manufacturing systems, need the kind of flexibility 61499 offers.
Why specifically?
They need to create highly tailored, adaptable solutions quickly. 61499 lets them distribute and map the control logic in ways the rigid, sequential model just can't support easily without major compromises. The framework gives them design freedom.
While the standard ensures consistency underneath.
Precisely. Freedom and consistency.
This has been incredibly helpful in, well, unpacking the layers here. Let's try and synthesize that critical distinction one last time, just to be crystal clear.
Okay.
61131. It solved the huge problem of standardizing sequential, mostly centralized control programming, got rid of vendor lock-in for the basic programming languages and functions, standardized syntax, and basic function blocks.
Correct. It tackled vendor fragmentation at the programming level.
And 61499.
It's the architectural blueprint. It tackles the problem of semantic inconsistency when you move into a distributed, reactive, event-driven world.
Okay.
It standardizes the model of computation itself, how these event-driven pieces of logic interact and cooperate reliably across all sorts of different hardware, whether that's on the plant floor or way up in the cloud.
So it provides the necessary structure for these modern, complex, data-driven automation systems.
That's the argument. It's the structure needed for Industry 4.0 and beyond.
Right. So the next time you, our listener, hear 61499 dismissed as just another programming language.
Remember this conversation.
Exactly. Remember, it's not about the specific lines of code. It's about that language of meaning, that semantic contract that lets the whole distributed system work together coherently.
Couldn't have said it better myself.
Oh.
Now, maybe a final provocative thought for you to chew on.
Please.
Okay. If we accept Jean-Baptiste Fontaine's idea that the real driver of progress is the speed and precision of agreements, whether that's between machines talking semantics on a network or human teams collaborating on designing those systems, then ask yourself, how much potential is still locked up right now in your own field, your own projects, simply because there isn't a shared formal semantic understanding of the complex processes you're trying to manage or orchestrate?
That's a powerful question. Lack of shared meaning as the bottleneck to innovation.
Something to think about.
Definitely something to think about. If you are engaging with IIoT, with distributed control, complex, flexible manufacturing, it seems the concepts behind 61499 are really where you need to start digging.
It seems that way, yes.
Well, this has been a fantastic deep dive. Thanks for joining us.
My pleasure.